When we talked about forces, we looked at what causes motion. Now let's go one step further by asking what enables an object to produce a force. In this video, we'll work out a definition of work and how it relates to energy, and then we'll use this concept of work to derive the formulas of various forms of energy, like, kinetic and gravitational potential. So, we're going to have some fun again. Einstein's first law of thermodynamics states that energy cannot be created or destroyed. It can only be converted from one form to another or transferred in the form of work and heat. That gives us a pretty clear definition of what work is. Right? It is a transfer of energy. Oh, heat, by the way, we'll talk about later on in thermodynamics. But right now we're going to focus on work. Now we want to work out the details of this definition soon. But before we even get there, we'll have to work out... Do you get it? Work out? Yeah, whatever. We have to work out the answer to the basic question of what's exchanging energy with what. For example, we have a dinosaur standing on the ground. Okay. We're interested in studying how this dinosaur is going to exchange energy with the environment. Well, first we need to define what our system is and what our environment is. As it turns out, in physics, when I say system, I really mean the object of interest. Everything around the system is called the environment. And together, the system and the environment make up the isolated superstructure. Remember that, because I used to get thrown off by this. I used to think the word system and isolated superstructure were actually the same thing, and I used it interchangeably. Now that would be wrong, strictly speaking. Now there are three types of systems. An isolated system does not exchange matter or energy with the environment. We're represented like that with two solid barriers between the system and the environment. In real life, there isn't a perfectly isolated system. And the closest thing I can imagine would be something floating, I guess, in space, not influenced by gravity or light. Like that's the ultimate loner or something. Maybe we should call them that. Instead of loners, we call them isolated systems. But I digress. A closed system is our second type. And a closed system exchanges energy but not matter with the environment, which will represent like this. And many things are closed systems. I guess maybe a computer could be one of them. It's not perfect though, I guess. And lastly, we have open systems. And we can probably already guess open systems exchange both energy and matter with the environment. So living things like our dinosaur and you and I would be open systems. And we're going to need this concept very soon, this concept of systems and environments and how they differentiate. For now, let's get back to work. Once again, get back to work. Yeah, I'm so funny. As I've already said, work is defined as the energy transferred into or out of a system. And that's opposed to converting energy from one form to another within the system. So, what's energy? Turns out the definition of energy is the capacity of the system to do work. It's like stored work, if you want to think about it that way. But if you kind of think this is a circular definition, one defining the other and the one defining the other and the other defining the other, bear with me. Let me give you an analogy that will make this a lot clearer. And if you love money, you're going to love this. Let's suppose we had a person with a certain amount of money. He will represent the system, and the amount of money that he has represents the amount of energy the system has. Now let's add in a bank. The bank, of course, as you know, as all banks do, have a lot of money too. The bank would represent the environment, and the environment also has a certain amount of energy. Let's give them each more energy to work with. Now, when the person deposits money or withdraws money from the bank, it's essentially the system transferring energy, which is work. If the person is depositing money, it's the system transferring energy to the environment. So we say the system is doing work on the environment. But if the person is withdrawing money, if the system is receiving energy from the environment, or the environment is doing work on the system. All of that is supposed to say if the person, I guess, exchange his dollars into some other form of currency. This over here would then be a form of energy conversion, converting one form of energy to another. Hopefully, that analogy does clear things up a bit. Now let's bring back the idea of systems and environment that we talked about in the last slide and talk about why that's so important in all this. The deal is, in a given situation, you get to set what the system and what the environment is. It's arbitrary. Let me give you an example. Let's say, it's a very crude drawing. Let's say we have here Galileo. Okay, this is a picture of Galileo. And he's throwing a punch. To begin with, we'll call the fist the system, and everything around it, including Galileo's body, would be the environment. And in this case, since the fist is going to gain in kinetic energy because it's moving outwards, being punched out, right? If it's gaining kinetic energy, then we'll say, of course, work is done because it must have gained energy from the rest of the environment, which is the rest of the body. But if, and we can do this, if we set the entire system, if we set the entire body as the system, now we are really only converting energy from one form to another. It's chemical potential energy from the body into kinetic energy of the fist. And in this case, there's no work done. There's just energy conversion, so work is zero. So the point is, whether or not the system does work or receives work from the environment depends on what you define the system to be. So far we've had a very conceptual understanding of work, and that's very important. But now let's move on to the mathy stuff. Alright, we're going to look at a formula to calculate for work. I'm just going to give it to you. Work equals force times displacement cosine theta. Theta over here is the angle between the force vector and the displacement vector. We're going to be looking at this in more detail later on. But for now, know that, well, work is a scalar quantity, a product of two vector quantities, but it's a scalar. I think you got that. I mean, transfer energy wouldn't have a direction, right? That's pretty straightforward. Also, I guess this is kind of interesting, the unit for work is joules. And just by analyzing this formula over here, we know the force has a unit of Newton and displacement has meters, and cosine theta is just a number. So a joule then would be equal to a Newton meter. That's a joule. We can further break down this Newton over here into, what is Newton? Mass times acceleration, kilograms meters squared per second squared. So both of these are ways of expressing the unit joule. Now let's use the formula in a couple of examples. If, for example, I had a person pushing a dinosaur to the right, and the dinosaur is moving to the right, now we have the force applied and the distance, the displacement, having a degree of 0. And cosine of 0 would then be 1. That makes work equals force times displacement. But if instead we have another person trying to push a dinosaur, but somehow the dinosaur is pushing the person back, and as always, the dinosaur is our system of interest, our object of interest. In this case, the person is exerting a force up the slope, but the displacement is down the slope. So there's 180 degrees between the two vectors, which makes cosine of 180 degrees as -1. So now work would be negative F delta D. What about a scenario like this? If a person is carrying a dinosaur and moving left and right, like that. So a person is applying a force in the upwards direction, but displacement is left and right. But since cosine of 90 degrees is 0, work isn't done at all. Now from all these we can generalize two common cases. If the work is positive, as in this case, we can interpret it as the environment does work on the system, which means the system receives work from the environment, so the system gains energy while the environment loses energy. And it makes sense because it's positive, right? Positive as in gaining energy, like gaining cash. And in our case, since our dinosaur is our system and the environment includes a person pushing him, the dinosaur is gaining in kinetic energy. The person is losing energy in the form of, I guess, chemical potential energy. Now, if the work is negative, we interpret it as the system doing work on the environment. So in this case, the system is losing total energy while the environment is gaining energy. And that'll be this case. So the system in this case, by going downwards, is losing potential energy, when the environment now, the person, including the environment, is now gaining in kinetic energy. Okay, that was a headful. I do hope you got that. Good luck.